Good morning everyone. Today we are going to see a topic about underwater sensor network. Underwater sensor network deployment. Before we enter into the topic, we will see brief introduction about what is underwater sensor network. Underwater sensor is nothing but a sensor network submerged in underwater. A network of self-powered sensor nodes, autonomous vehicle deployed underwater and performing collaborative tasks using acoustic links. Each nodes deployed underwater and they communicate with each other using acoustics. Underwater acoustic communication is a technique of sending and receiving messages below water. Why we are using underwater sensor network? Because the Earth's surface contains 75% of water covered with form of rivers, canals, seas, oceans, etc. Plenty of precious resources lie underwater which are required to explode. Underwater sensor network is a fusion of wireless technology with extremely small micro-mechanical sensor technology having smart sensing, intelligent computing and communication capabilities. Then what are the applications in the underwater sensor network? There are several applications: open sampling network, environment monitoring, undersea exploration, disaster prevention, equipment monitoring, assisted navigation. What are the components used in the underwater sensor network? And generally we use a sensor and Aquacom underwater modem, LinkQuest underwater sensor nodes, AUV autonomous underwater vehicle, drifters, gliders. How underwater sensor works? Underwater sensor network is a network of autonomous sensor nodes which are spatially distributed underwater to sense water related properties such as quality, temperature, pressure. Underwater communication is mainly done with a set of nodes transmitting their data to buoyant gateway. Gateway nodes that delay the relay of nearest coastal monitoring and control station, also called a remote station. The communication between underwater and coastal, this communication is called underwater communication. Now we will move on to the underwater sensor network deployment. Underwater sensor deployment. The deployment we saw about what is underwater sensor network. Now the deployment is means nothing but the arrangement of nodes in the how we will arrange the nodes in underwater, in which type. The discussing about the arrangement of sensors in underwater is called underwater sensor network deployment. The node deployment supports many fundamental network services such as network topology control, routing and boundary detection. The challenges, what are the challenges we face the deployment? The complex deployment environment, especially in 3D space. Underwater acoustic channel characteristics, large propagation delay, high error rate, multipath effect, limited battery power available in nodes. Our main goal, the node deployment algorithm need to address the adverse channel condition, water mobility, energy efficiency of the sensor nodes. Underwater sensor network deployment depends upon the mobility. We divide the deployment into three types: static deployment, self-adjustment deployment, movement assisted deployment. Within the static deployment, there are two classification: random, regular. Within self-adjustment deployment, two classification: uniform coverage, non-uniform coverage. In static underwater sensor network deployment, we see two classification: random, regular. We see about a random deployment. The most practical way of deploying the sensor nodes. The random deployment becomes the only option if there is no prior knowledge of the to be monitored region. Deterministic deployment is very risky of infeasible. A regular deployment, the sensor nodes are anchored at the vertex of polygons or polyhedrons. Advantages of a static underwater sensor network deployment. The advantages, what are the advantages we see means static underwater sensor deployment algorithms enable easy and energy efficient deployment strategy. They do not need any mobile nodes to participate in the deployment periodically. Disadvantage, they cannot deal with the real-time event processing in large scale. Next is self-adjust underwater sensor deployment. The sensor nodes are capable of adjusting their position in the underwater after initial deployment. By the name itself is self-adjust. After we deploying, it can adjust its position. Underwater after initial deployment to satisfy certain requirements. Each sensor node is attached to the floating buoyancy. Sensor nodes can adjust their depth by controlling the length of the wires. Advantages: the depth adjustment system enables the node to be positioned with the desired topology, which improves the network connectivity over the monitored region. The relocated sensor nodes at the different depth based on the local agreements can effectively reduce the coverage overlaps among the neighboring nodes. Within the self-adjust deployment, we see two classification: uniform coverage, non-uniform coverage. Uniform coverage. The sensor nodes are initially deployed at the bottom of the ocean. Each sensor node is assigned the target depth. The nodes float to the desired position to achieve the target cover ratio. Non-uniform coverage. Sensor nodes adjust their position according to the dynamic environment and targets. The event area is covered in an optical manner by using optimized algorithms such as game theory and multi-objective nonlinear optimization. A movement assisted underwater sensor network. Before we see that self-adjust static. There is a vast difference between self-adjusted static and movement assist underwater. Because we use automated undersea vehicles in the movement assist sensor network. The AUV, ROV remotely operated vehicles are deployed with other sensor nodes. They patrol over the monitored region and under predefined trajectory to cooperate with the sensor nodes to execute their desired task. Sensor nodes can be attached to the mobile nodes and they can be shifted to some desirable position after initial deployment. The self-deployment of sensors for maximized coverage in underwater acoustic sensor network. The current node deployment in underwater sensor network is mostly manual and centralized. The sensors are placed manually with tethers from the surface station or anchors from seabed. Such a deployment may not be feasible in application where deployment region is not accessible due to enemy threats or existence of mines in underwater tactical surveillance applications. Such a deployment scheme requires additional time and cost, particularly when the volume of a monitored region is larger. There is a need to drop the sensor nodes from a flying vehicle or from a fixed ship to the area of interest. This is a diagram how arrangement occur deployed under say the proposed scheme consists of 4 phases: clustering, grouping, depth adjustment, additional adjustment. How they are arranging depends upon the naming into 4 phases: clustering, grouping, depth adjustment, additional rounds. Clustering: after initial random deployment, the sensor nodes are clustered based on their node IDs. Here the cluster occurs on their node ID. They are clustered depends upon node ID. Each node in a neighborhood picks the highest ID in that neighborhood as its cluster's ID. The node with the highest ID is the leader of the cluster. Here we see how the clustering of sensor nodes occur created. Grouping: once the nodes are clustered, the cluster leaders need to determine the possible coverage overlaps within a cluster. Nodes are grouped with each cluster based on their average coverage overlaps with their neighbors. The edge between two nodes indicates that there is a sensing coverage overlap among the two nodes, and they need to be sent to different depth to eliminate this overlap. At the end of this phase, these nodes need to have different group IDs. The cluster leader makes sure that no two nodes having an edge shares the same group ID. Here we see how grouping occurs. Grouping of nodes based on sensing coverage overlaps. Then depth adjustment. To improve coverage overlaps and overall 3D coverage, the depth that will be assigned to each group are computed as the space between two groups is d divided by g plus 1, where d determines the depth of water and g number of groups. This spacing makes sure that each layer is d divided by g plus 1 distance away from each other. The top layer is within the distance from the surface and the bottom layer is within the distance from the ocean bottom. The calculation of the depth is done by the cluster leader and the depths are sent to each node within the cluster. Additional round. After initial movement, the nodes from different clusters are assigned the same depth and can still have coverage overlaps. Nodes continue to attempt to move away from each other vertically. The movement will need to be stopped when there is no significant improvement for coverage or a certain number of rounds is achieved. Impacts of a deployment strategy on localization performance in underwater acoustic sensor network. In this work, the impact of different deployment schemes on localization and network connectivity are investigated. The type of deployment schemes considered in underwater sensor network are random deployment, cube deployment, regular tetrahedron deployment. The sensor nodes are deployed at different depth depending on the deployment scheme. Random deployment. The anchor nodes are deployed randomly in a 3D monitored region. Then the ordinary sensor nodes are deployed randomly in 3D monitored region. In this work, the impact of different deployment schemes on localization and network connectivity are investigated. And the types of deployment schemes are considered in underwater sensor network are random deployment, cube deployment, regular tetrahedron. Oh, sorry, the PPT is repeated. Here we see the cube deployment, one cube unit, a random deployment, one regular tetrahedron unit. The first one is a cube deployment. This is one cube unit This is within a cube. Then the nodes are arranged in a random manner, so it's called a random deployment. The fourth one is one regular tetrahedron unit. Here we see the tetrahedron. Within this, the nodes are arranged. Simulation parameters, localization ratio, the ratio of the number of localized ordinary nodes to the total number of ordinary nodes. The regular tetrahedron deployment scheme outperforms the other schemes. Localization error, the average distance between the estimated coordinates and real coordinates. The regular tetrahedron deployment scheme has a small localization area. The network connectivity, the ratio of number of sensor nodes that can communicate with other sensor nodes to the total number of sensor nodes. The network connectivity performance of the regular tetrahedron deployment scheme is slightly better. Thank you. That's all we see about the underwater sensor network deployment.